The first homework is due when? Tuesday. I think what I'm going to do, because we're going to get to some of the ideas on by Monday, I want you to have a little bit more time to think about yourself. I talked to the professor, who's me, and that date is going to be extended by 1 day. So it's actually going to be due now on Wednesday. So homework. It's due Wednesday. So Tuesday. Then I'll give you a little bit more time to come by and ask if you have any questions on things like that. Because I don't like finishing a topic and then immediately having homework due. It's especially at this level. When if you take my upper level courses, I don't worry as much about that because you're all grown up. But right now you're not, so I don't mind cutting some slack. The other thing is, when is the homework due?
Next.
Okay, so join my mistake because I changed it. But when is it due? I changed the date. When is it due?
At the beginning of class.
At the beginning of class. Okay, so I'll come in, I'll say, hand in your homework, I'll take your homework, the solutions go out. If you forget your homework and at your dorm, that's fine, go get it, turn it to me. I'll grade it, but that will be recorded as a 0. Okay, just because, and I'm going to be really, really draconian about it. Because I found out if I don't, then it's just bad things happen. It's just too hard to keep track of. And also, it's just not really helping you. You really have to get in that mindset of just, it's due when it's due. Okay, so I'm going to be really quite unpleasant about it. You could have the most reasonable, a meteorite destroyed my house. And, I was out all last night, trying to buy a campfire, keeping myself warm. And I need just a couple more minutes to just write it on paper, all perfectly legitimate, but it's due at the beginning of class. And if that happened to occur after, it doesn't matter. Okay, all my family died in a tornado. I'm sorry to hear that. Okay, that's awful. Okay, I will say a prayer for your family, but the homework is due at the beginning of class. Okay, and I'm going to be just remarkably draconian about it. Okay, so you can have the most legitimate excuse, and just that's the way it is. Okay, so what I want to do now is continue to do some stuff with acceleration. And then I want to kind of reverse the process. I want to say, well, what happens if you have an acceleration? Can you figure out what the velocity is? And can you figure out what the position is? Because that's going to be actually a big thing you're going to do. And if you're an engineer, that's important because often that's what you're trying to measure. You might have some device and some rocket that's going to measure the acceleration. And then from that acceleration data, you can figure out what the velocity and the position is of that object at any time. So I want to do that. Okay, so let's go back and talk about our acceleration. Okay, so we send an object here. This is position x1. It has some velocity v1. This is at time t1. And it moves down the road. It's here. This is x2. This is v2. This is t2. And what we did is that we have the idea of average velocity. Oh, I'm sorry. Either notation. Okay, how do we define average velocity again? Delta velocity, delta x, or delta t. Yes. And then we define a new one, average velocity. Okay, now go on with your thing. Yeah. That's our delta v over delta t. And we made a graph of this here. If I plot my x versus time, we go like this. Here's my t1. Here's my x1. Here's my t2. Here's my x2. Okay. Graphically, what did we say the average velocity is? Graphically?
So secant.
Slope of the secant. Well, what does it mean to be a secant? You have a curve, and what do you do to the curve? Yeah, you put 2 points on here, draw the straight line between the two. That's a secant. But again, if it tried, it could. Then it would be the c could. Okay, good to know. Okay, so here's our straight line connecting the two. Here's our secant. And then the slope of the secant. It's then going to be our delta x over delta t. But then what did we do? Last time we then set up the velocity versus time graph. And then another random graph like this. Here's T1, here's our V1, here's our T2, here's our V2. And then graphically, what did we say then about then the average acceleration? The average acceleration graphically is the slope of the secant in the V versus t graph. So I draw my little secant again. So here's this secant. And the slope, the secant in this case, is then as this delta V over delta T. Again, here's my change in velocity. And here's my change in time. Okay. Any questions with that? That all make sense? All good? Okay. That is still staying in focus. Good. Okay, it doesn't always stay in focus. Okay, now how did we then get how did I get the actual velocity at this point here? What did I do to this over here? So this is, if I want to know the velocity right here, I could say the velocity right here is approximately equal to this average velocity. But what did we do to make that approximation better and better and better?
Small, the distance between the two.
Yeah, so that we made the delta T, we took the T2 here and made it smaller and closer to T1. In other words, we made that delta T smaller and smaller and smaller and smaller. So what we can do is that to find the actual, or what's another word for the word actual? Starts with an I. Instantaneous. Okay. So actual or instantaneous velocity. It's going to be what? It's going to be the limit as this delta T goes to 0 here. Okay. And formally, this is nothing but the definition of a. Ooh, yell at me. Okay, yell at me here first. Don't let me get away with garbage. Tell me why you should yell at me here. -2 for the teacher. Yeah, that should not be delta V, that should be delta X. But watch. Since I'm using the superior technology that I call marker, not PowerPoint. Ha! Okay, what can I do? I'm not done. Try doing that with PowerPoint. You can't. Why? Because the marker is superior to PowerPoint. Good to know. Okay, and then we said that's formally the definition of our what? dx dt. Now this dx, well, anything with a d in it, what does a mathematician call that? This one also starts with an I? This is the infinitesimal. And what does an infinitesimal mean? It's just like a delta, but it's remarkably small. It's this limit as it actually goes to 0. Okay. So what does this mean? If you have a car whizzing by here like this, if I want the velocity of it right here, I take the tiny little distance it moves, dx. Okay, and I divide it by the tiny time it takes to make that tiny little, to move that tiny little distance, dt. And that ratio there is what I mean by velocity. Does that make sense? But hey, again, in physics, you learn one trick and you beat the trick to death. Okay, so if I want the actual velocity at the actual acceleration at this point here, I can say the acceleration at this point here, the actual acceleration, is approximately the average acceleration. Okay, now that's a crappy approximation. But what can I do to that to make it better and better and better? Again, it's exactly what you think it's going to be. Yeah, if I take this T2 and move it closer and closer and closer to here, meaning take that delta T, make it smaller, what's going to happen is that's going to be the actual instantaneous acceleration at that point. What's going to happen here is come over here. Is that fine? The actual or instantaneous acceleration at time t let delta t go to 0. So you're going to say the actual acceleration, the average, I'm sorry. Actual acceleration is going to be the limit. It's delta t goes to 0 of my average velocity, my average acceleration. Does that make sense? So if I have a car whizzing by here, and if I want to know the acceleration here, I take its velocity here, and I take its velocity here to some two little points away from each other. I take the difference there. That's my delta v, and I divide it by how long it takes that object to move from here to there. Okay. If I let that delta t become smaller and smaller and smaller, that's going to be the actual acceleration at a point. And so this is nothing but our friend. How'd you write that for the rest of your life?
The acceleration average.
That's not average yet, because now we're taking that. dv dt. Yeah, this is nothing but the definition of a derivative. For the rest of your life, if somebody asks you what is the velocity, your response will be the x dt. And for the rest of your life, if anyone asks you what the acceleration is, the answer is that's always true, is dv dt. That is always, 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 always true. That never goes away. Even if you go to quantum mechanics, even if you go to special relativity, it is always those expressions. Even general too. Starts getting a little funky, but it's still the same. Okay. Is there any questions for that? Okay, mathematically now graphically, what is this? The XCT is graphically what on this graph? It is the not anymore. That was the tangent. Tangent. Now it's the tangent. Okay. So in this case here, this is the slope of the tangent line on the x versus t graph. Okay. This over here, what does this become over here graphically now? Slope of the, not anymore, slope of the tangent line on the v versus t graph. This one here, this is the slope of the tangent line. On the v versus t graph. Okay, makes sense? If we put these two together, I say that A is dv dt. Well, what is V? Let's make that look like a V. Well, what is V? Always, always, always. The xct. The derivative of a derivative is what? The second derivative. Okay. And so this is just going to be nothing but this. So your acceleration is also the second derivative of your position at this other time. And mathematically, what does the mathematician call this? That's telling you how your slope is changing, right? This is telling you this is your slope of your x versus t graph. That's what this is. And what does this tell you then? This is telling you how that slope is changing with time. And so what does the mathematician call the rate of change of slope? The curvature. So this right here, this is your the curvature of the x versus t graph. Okay, that makes sense. So what I want to do is I want to do a graphical example of this, and let me say a little bit more about this acceleration here before we do an example. So there's an interesting case here. So take the special case of constant acceleration. it turns out in many things in life, your acceleration is going to be a constant. We're going to find out if you drop an object that near the surface of the Earth, that acceleration is constant. We use air tracks on Monday. Lab will start on Monday. We're going to find constant acceleration as well. And we'll look at that. So let's take the special case of constant acceleration. Okay, I'm going to have you do some math in your head. Okay, I'm going to give you 5 numbers, and without a calculator, I want you to tell me what the average of these are. Ready for this? 80 is the first number. 80 is the second number. 80 is the third number. 80 is the fourth number. And 80 is the fifth number. What is the average of these crazy numbers?
That's kind of hard.
I know. It's like, come on, give me something hard. Okay. It's going to be 80. Okay. So if you have a constant value, the average value and the average is going to be the same as the number. Does that make sense? So if A is a constant, I can say that the average of A is the actual value of A. They're the same. And what do we know about the average of acceleration? The average acceleration is always, it's the fundamental definition of this. Not quite. Change in V over change. The D means you made the change small. Okay. So this is going to be delta V over delta T. Okay. I just want to give you a sense of what this means here. So let's see what this means here. An object is accelerating. So if, let's say the acceleration is -10. Okay, and let's say the initial velocity is going to be, let's say 30 meters a second. Okay. Let's find the velocity of the object at t equals 1, 2, 3, and 4 seconds. Should be units on this too. Meters per second. Okay. So you tell me, after 1 second, so let's let delta t. So delta t here is going to be 1 second here. So after 1 second, what is the new velocity? Well, does that make sense? Let's go through and do it formally. So if I had A, which is going to be this delta V over delta T, the change in velocity is A delta T. That's how much the velocity changes. So what does this mean here? The acceleration is -10. Our change in time is 1. So the change in velocity is 10 meters a second. Okay. So the new velocity is going to equal the old velocity plus the change in velocity. So our old velocity is what? It's this 30. Our change in velocity is this -10. Now it's 20 meters a second. Okay. What would be the velocity of this in another second, at 2 seconds? So this would be the velocity at 1 second, right? This is the velocity here. So old velocity is the velocity at 0, and this is 0. What's the new velocity at 2 seconds? Yeah, we take now the velocity then at what? At 1 second here, which is now 2. We add the change in velocity, and the change in velocity is going to be this exact same value, -10. Now it's moving at 10 meters a second. Does that make sense? Okay, another second. So now let's do the velocity at 3 seconds. We take our old velocity, which is now this one, 10. We add the change in velocity -10. Now it's 0. And finish it up. Yeah. If I want the new velocity at 4 seconds, it's going to be our old velocity, which is now 0, plus our change in velocity. This is now minus 10. So what happens to this? Let's say this is a car going this way. So if my car is going this way, what's the initial velocity? 30. After 1 second, let's say it moves to here. Now what is its speed? Velocity? 20. After another second, it's here. So I'm going 10. Now over here, stops. Now what does it mean? What happens now? It's now going this way. And if I'd ask at 5 seconds, what would then happen? Now it'd be minus 20. Another second, minus 30, minus 40. So it's speeding up this way here. So you have to be a little careful here. You see a negative acceleration. What do people often say about a negative acceleration? They say the object is slowing down, or there's another word that people often say. Starts with the D. Deaccelerating. Okay? So you say the object is deaccelerating. And if I say an object is deaccelerating, what does that sound like? Just from everyday life. The object is slowing up. Okay, you have to be careful, and this is where you have to be careful with the physics words. Is this object slowing up?
It's moving in the opposite direction.
It's kind of a yes or no. I mean, saying no is right. Saying yes is kind of right. Okay. Why could you say kind of yes? But I don't want you to say yes. I want you to say what Leaf said.
It's the opposite of velocity.
Yeah, so initially what's happening to the object? Is the object initially slowing up? Yeah, right. It's going initially, it started at 30. Now it's going 20, 10, and 0. So it is slowing up. But now what's happening? It's speeding up, but it's speeding up to the left. Okay. So you have to be really careful with these things. You don't think, oh, this means that the object is slowing up. Well, it's going to be initially slowing up if it's initially going this way. But eventually what's going to happen, it's going to start speeding up this way. Okay, does that make sense? And you can see the same thing. Let's do a crazy experiment. Done. Okay. If you throw a rock up in the air, what happens? Slows up, slows up, slows up more, momentarily stops. And then what happens? It starts going this way, but as it starts going this way, what does it do? Faster, 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 faster as it falls. Okay. We're going to find this is called free fall, and it turns out that free fall is another example of constant acceleration, but we don't know that yet. Okay. So you have to be a little careful with these things here. Now, what would happen if the initial velocity of this object were minus 30? If the initial velocity were minus 30, what would then the car be doing? It's initially going this way at minus 30. After 1 second, it's here. What's it doing now? Minus 40, then minus 50. So give me a real life example involving a car where you could have that. I don't recommend doing this, but yeah.
Backing out of the driveway.
Yeah. Okay, so let's say you hop in the car, you put it in reverse, and you step on the gas. I don't recommend that. Okay. But what would happen? Like that, really quite quick. Okay. Give me an example. I don't recommend this one either. Where could you have an example like this involving a car? I've heard you can't actually do this. I've heard it's actually engineerically with modern cars impossible to do. Don't try this. Okay. So where could you actually have something like this happen in a car? Let's say your car is going this way. Then what could you do to then make it go backward like this? Put it in reverse. And I've heard with a modern car, you can't do that. That if you're going this way and try to throw it in reverse, it doesn't work. Do not try this with your car or your parents' car or your roommate's car. Let's not do that experiment. If it can be done, it probably would destroy the transmission.
Use a rental.
Okay. And do not try it with a rental either. Do not try this with any type of car. But this would be the case if you could do it. The car is going this way, you throw the car in reverse. Now it has negative acceleration, then it slow up, slow up, slow up, momentarily stop, and then it start accelerating this way. That makes sense? Questions? Okay, let's try a qualitative example then. And then I want to show you how to do this a little more formally. Well, let me give you another example. So let's say, what would this one be? Let's say I have Here's a traffic light. Let's say this is red. And the car is going this way. I want you to give me the initial velocity. The initial velocity, we're going to start calling V naught. Okay, I want you to say whether this the initial velocity is positive, negative, or zero. Then I also want you to give me the acceleration. By the acceleration, I mean, I want you to tell me whether it's positive, negative, or zero. So, cars coming, traffic light red. Tell me about the initial velocity and tell me about the acceleration. Give me the signs. Okay, I saw her first. Yes.
Velocities, positive accelerations.
How come?
This is all-
I agree. It'd be positive because
It's still moving.
the car is going to the right. Okay, so the car is going to the right. Anything going to the right, we call positive velocity. Why is it negative?
It's going down to the right.
It's slowing down, right? So this is basically slowing down. But there's a part B to this question. Turns out at the same time, there's a car going this way, the left. Okay. I want you to repeat it for this car here. Yep,
It has negative velocity
a
and
negative initial velocity, how come?
because it's moving left.
Okay, so the initial velocity being up. Going to the left. So it's negative.
And I'm assuming they're going to stop at the light, so it's slowing down, which is negative.
So everyone agree the acceleration would be negative because it's slowing down? I'm hearing a no. Others? Or take an average and then that's what it will be. What would happen if it had a negative acceleration?
Oh, that's right, it'd be going.
That means that every second, the velocity would change by some negative amount. So what would this car then be doing? It'd be speeding up this way in the negative direction. So this car is going this way with a negative velocity. What has to be the acceleration? It has to be positive so that the change in velocity means that this would be slowing up. That makes sense? So let me give you an example here. Let's say that this car here has an initial velocity of minus 30. Let's say the acceleration of 1. Okay. What does that mean? That means just like we had before, the acceleration, which is 1, is a change in v over a change in t. So a change in v, it's going to be this 1 times delta t. So this is going to be 1. I'm sorry, 10. 1. So our change in is, that's kind of a sad thing, but this will work. So the change in velocity is going to be 1. So after 1 second, what is the new velocity in the car? This is 9, maybe 29 would be the velocity now at 1 second. Would be the original velocity of minus 30 plus a change in velocity plus 1. That would be going at minus 29. So it's actually slowing up. Okay, so you have to be a little, whether something is speeding up or slowing down depends on what we define to be positive. Okay. And what we do is that once we get a direction for positive, we keep that for the entire problem. Okay, so we said this way is positive. Why? Because this way is positive. That's what we're going to say. Yep.
Does this change with random dimensions? Like,
I think, does this change with what?
because it's only one dimensional, is that why? It's
Yeah, so we're only doing motion this way or this way. Okay, in a little bit, meaning next week, we're going to start doing 2 dimensions. Okay, and what we're going to do, we're going to need 2 directions and the positiveness. So we're going to say anything going to the right is positive, then anything going up is positive. And then we're going to figure out how to split up the problem. Okay, and then I'll start getting rise to vectors and stuff like this. But we're not there yet. Does that make sense? Okay. So these concepts here live with it turns out that actually this is, I think, where the class actually starts going south. Sometimes right at really basic ideas of what it means to have a positive velocity and a positive acceleration or a negative velocity or negative acceleration. Sometimes that really basic idea is not really understood. And that's when things can start going south. So just start thinking about it every day. How let's do a thought experiment. Stand up on your chairs. Okay. And let's, so we don't run into people, let's turn this way here. Okay, so what would we look like? Let's say we have an initial velocity that's positive and a positive acceleration. If I were to say walk this way, what would that be? If I have our initial velocity is positive and our initial acceleration negative. I'm sorry, positive. How would we walk? We'd be going initially to the right. And as we walk to the right, what would we be doing? So how do you have to do that? Try to do it. It's going to be like, it's actually really, really hard to do. Okay. We're all going to look stupid together. We're going to look stupid a lot in this class here. Okay, so let's try doing it this way, speeding up. You might want to turn so you don't show yourself. Okay.
No.
Okay, so let's try this again. So we walk like this, and then we speed up and speed up, and then it's actually really hard. Okay. Okay. Now, what would happen if instead we had that? So we'd be walking this way, then what would we do? Slow up, slow up, slow up, slow up, momentarily stop, and then what? Start going like this, actually faster and faster and faster. That's actually hard to do. That makes sense? So suppose we did it vertically. Right, it'd be kind of down here, okay? Then what we go up, slow up, slow up, slow up, slow up, slow up, momentarily stop, and go down like this, faster and faster. Or we could just done. Crazy. Okay, what would happen if we did this? What would that be? Yeah, there's no acceleration, meaning the velocity doesn't change. So this is just, walking down the street. Kind of cool. Okay, we're done. So you can sit back down. See, if I end up teaching the second semester of the class, and I don't know if I will be, it depends on what the teacher does. We'll do waves, electromagnetic waves. I'll teach you all how to do the wave dance. So we'll do the wave dance together, but that's next semester. And we'll all look stupid during the wave dance.
Wait, do so again.
Well, we can start. Okay, here we can. Okay, take your hands like this. Okay, and what we're gonna do, we're gonna go up, down like this. This is gonna be the electric field, and then this is the magnetic field. So what you have to do is, you're gonna have to walk at the same time. So what we're gonna do is gonna be like. That's remarkable. Yes, and we're all gonna look stupid together. And if you take my course in optics, then I show you how to do the circular polarized version of that. And that turns out to be hard as hell. Oh, because that one's going to be where you're going to have basically throughout a phase. So you don't have this, you have no. See, it's really hard to do. It's hard. It's just really hard. Okay, to do the circular polarization while you walk. That's hard. Okay, so you're already ready for seconds. You're ahead of the group.
So for the car problem, the acceleration would be negative because it's going to the left.
Because a change in velocity is negative. So in other words, if the car is going this way and slowing up, okay, so meaning the change, if your acceleration is negative, that means your change in the velocity is negative. Okay? So what that means here, if the object's initially going to the right, the change is negative, meaning it's going to slow up initially. So if I'm going this way, I'm going to slow up, slow up, slow up, slow up, momentarily stop. Now my change in velocity is so negative, which is the left direction. So it's going to go like that, but since it remains negative, we're going to start speeding up in this direction, even though I have a negative acceleration.
So is that always gonna be true then? So like
I mean, meaning always, once you know this idea here, depending on how the car initially starts up or whatever we're dealing with, you can figure out any of it. It'll always be true. Okay. And we're going to be doing a whole bunch of examples of this. Okay. And we're going to find little buzzwords. We're going to find words when we do problems that's going to say things like the velocity of an object is 3 meters a second. Okay, if you had a problem that said the velocity of an object is 3 meters a second, what would it mean then about the acceleration? Constant, how come? Because what does it not say? The initial velocity is 3 meters a second. You just say the velocity is 3 meters a second. What does it mean? It's 3 meters a second. It's not changing. If it's not changing, the acceleration has to be 0. And that's going to have, when we start getting forces, that's going to become really, really important, because that's going to mean that's going to mean the total forces acting on the system is 0. And we'll see the implication of that later on. Okay, so now let's do a qualitative picture here. Okay, so let's draw a little x versus t graph. I'm just going to make something up. I'm going to have it go like this. I just made this up. And I want a qualitative, so this is an example. I want you to draw a qualitative V versus T graph and A versus T graph. This is V versus T, and make it smaller because I want them all underneath each other. Okay. So let's say you had this. You have an X versus T graph, and I want qualitative versions of each of these here. Okay. What would you do? What do you know about the velocity for the rest of your life? It is always. Okay, yes, but tinker with it. If you're going to say change in X over change in time, how do you have to tinker with it? That change has to be tiny. If that change is tiny, then mathematically, how do we write that? dv is going to be some sort of differential here. So the velocity for the rest of your life is always, always, always what? D x ct. And mathematically, the xct is always, always, always what? Graphically? The? Not almost, tinker with it. Tangent of the x versus t graph. Okay. So if I want that, what did I say? Whenever you do these qualitative graphs here like this, what's the first thing you do before you do anything else? You look for the zeros in this graph here, and the zeros in this graph here are going to correspond to the
peaks.
Or the maximums or the minimums. Remember, if you have a max or min in a graph, those slopes are 0, those tangent lines. Okay, yep.
Why, like, can't we just say, it's like the prime of the.
You can, but the primes, that notation is primarily used by the mathematicians, and it's not wrong. So if you wanted to, you could say, oh, this is just x prime. Perfectly acceptable notation. Usually in physics and engineering, that's rarely done. Okay. Different areas have different things. Actually, okay, don't use this notation. Not at your age. You're too young for this notation. Okay. What happens is when you get more advanced stuff, it turns out you're going to call x dot. A dot will only refer to a time derivative. So usually, physicists are going to put dots on things, but don't at this level here in 125, and for a while.
You don't use dots for, the velocity.
A dot is only going to refer to basically a time derivative. And again, don't even worry about that notation.
Yeah, for like
Okay.
isn't it I, J, and K?
That's going to be something else. And that dot there is going to refer to a dot product, which is going to be a type of vector multiplication that we don't know yet. But we will. Okay. Okay, so it's going to be the xct, and what we're going to do, we're going to look at the maximums and minimums here, meaning of the function. So right here, that's a minimum, so that slope looks like a 0. So once I get to this point, what do? So at this time here, t, I have no slope here. So what do I do now on this graph? Yeah, at that corresponding t. So I draw this corresponding t down here, and I put that 0 there. Now what do?
Same thing.
Same thing over here. At this time here, this is the maximum, so that's no slope. And I carry that maximum down to here. Those zeros are going to anchor your graph. That's the first thing you do with any of these, put down your zeros. Okay? Now, what's the next step? You start on this side and you work like this. Okay? So we start over here, I draw a slope. Tell me about that slope. It is negative. And so where do I go to in this graph here? I go below the axis here and I put a little dot here. That t equals 0, I have no slope. I'm sorry, I have a negative slope. So I have a negative value here. Now what's going to happen when I'm over here at this spot? This slope is
Negative.
negative, but how does it compare to this one over here? It's not as steep. So what am I going to do here then? Yeah, it's going to be still negative, but it's not going to be as negative. So this value here, this time here, I have something that's less negative. Now what about over here at this spot?
It's positive.
This is
Oh, that one.
slightly positive. What about it? So I draw then at this time here. I draw something positive at this spot right here. Now look at that slope. It's more positive. So I come here, I have that point. Now what about at this point here? More positive, but
That's positive.
less positive than here. So I have that here. And then if I come over here, what do I have? At this point here, I have something negative. So I have this guy. Let's say here. Yeah, it looks like it's less negative. Okay. Well, let's do something a little more negative. This is more negative here. And then this is less negative here. And then this is really almost 0 here. So if I were to draw this guy here, you have something like that. It's a qualitative graph. So if you three work together here, you're going to have something that looks like this, but it might be a little more funky looking depending on how you look at it. The main thing that everyone's going to have the same is that this point here and this point here have to be zeros. Now somebody else might have something more steep like this or more shallow like this. They're all fine. It's a qualitative graph. Does that make sense? Okay, now go down to here on this part. So if I want an A versus T graph, what is the acceleration for the rest of your life now?
DVDT.
dv dt. And dv dt is graphically is a
It's sort of
slope of the tangent line of the V versus T graph. Hey, so how do I draw that? In the words of Scooby-Doo, ring, Randy, same thing, Shaggy. Meaning you look for your zeros again. Okay? So where do I have my zeros here? I have this point over here. On this one, let me change my color. This one I have this 0. That corresponds to my 0 here. And this one here, I look at my slope here. That's my 0 here. So I draw my 0 here like that. That makes sense. Questions? Hey, now what? Yeah, once you get your zeros in here and get this anchored here, then you start on this side and you work all the way across. So if I look at the slope right here, what can you say about the slope here? It's positive, so I have something like this. Okay. What about over here? It's positive, and how do the values compare? It's kind of close. So I might have something here like this, but as I start getting toward this peak here, what about the slope over here? How does it compare to here? It looks less positive. So this value, you're going to have something less positive. Like this. Then over here,
negative.
negative slope. Here, more negative. And if I'm here, right there,
Almost less negative.
Yeah, it's gonna be something less negative here, like it's qualitative, so it's kind of hard to tell exactly. And if I hop over here,
That's awesome.
I'm gonna have something positive in here. Maybe a drop more positive than if I drop over here. Probably a little less negative. I mean, a little less positive. So you get something that kind of looks like. Gonna be something like that. Always draw a smooth curve through them. Don't draw something jaggedy. You never have like jaggedy things. And why would I not have something jaggedy? This is more of a math question. I'm thinking a little more math. If this is nice and smooth, what can you then say about the derivatives? They're going to have nice and smooth shapes too. The fact that this is nice and smooth means that these are going to be, they're not going to be, they're not going to be something like that. You're going to have some nice smooth shape to those. Does that make sense? Questions? Okay, now what we want to do is we want to start reversing the process. I want to start giving you an acceleration, and I want you to figure out what the velocity versus time is, and then what the position versus time is as well. So let's ask this question. Okay, so how can we find velocity versus time and position versus time given the acceleration of an object? So as an example here, let's say I tell you the acceleration equals 3 times t. Why does the acceleration equal that? I made it up. There's absolutely no reason for this. Okay. And I got to know that the object has an initial velocity of 1 meter a second and an initial position. Let's say 2 meters. I want you to find the velocity as a function of time and the position as a function of time. I'll start this up, and then what we'll do, we'll finish it on Monday. So how would you have to start? This is going to often be the hardest part here. So what do you know about the acceleration? Always, always, always. It is, for the rest of your life, dv dt. So you know the acceleration is dv dt. But in this case here, the acceleration is, because I just magically pulled it out of thin air, 3t. So this tells me that 3t equals dv dt. Now, if I want you to solve for v, okay, I'm going to send you back to Calc 1 or Calc 2, wherever you do this. If you're to see this expression here in calculus, and they say solve for v, what would you do? You'd integrate it, but let's put in all the stuff to have really, really good mathematics, okay? So mathematically, what would you do? You'd multiply both sides by dt. I come here and multiply both sides by dt. So this would give me 3t dt equals, and what happens? The dt's would cancel here, dv. Then what would you do? Now in that form, you can now, you've already said it, we can now integrate it in this form. So in this form here, we can now integrate it. And where would our time go from? We're always going to start with the time of what? What do you think we're usually going to say the initial time is? 0. We're going to say 0. And in this case here, the time t equals 0, what did we say the initial velocity is? Yeah, I magically said it's equal to 1. Why? I made that out of thin air. So time t equals 0, this is 1. And then when are we gonna, if I want a generic expression, to what time am I gonna integrate this to? To a time of, if I want a generic expression. I'm gonna say t. And at a generic time t, the generic velocity is gonna be v. Okay, so we'll stop here today. We'll pick up this point here on Monday. And we're gonna find out we can do a lot with this. Okay, have a good day.